I built a whole full stack application for my for the startup. And then for Amazon, I was working on focusing microservices on the backend side. And on Google, I also building the RPC service. And I kind of like get a taste of different aspects of the tech. And now as a developer, you have to, build more like architecture level things. So because I've been tasting different aspect of it, and then now it makes so much sense for me to connect the dots and understand when I try to build like a design architecture. I think all the experience, so now when I look back, I think all the experience can helps me to understand technology easily and then learn the things.
So I'm going to click run simulation in our system.
Yeah.
And we're actually going to see a simulation kick off with 1,000 AI agents running a marathon through Las Vegas in real time.
Actually, 1,000 AI agent. Wow.
That's right. 1,000 individual sessions that are all, communicating together with a simulator and a planner. So, what we're looking at here is a front end that is communicating with a message passing gateway. We're going to dive into the architecture in a little bit. And I'll just follow the leader here just for fun. Each of these little dots is a runner agent session, and we're constantly checking on them with regard to their hydration levels and their velocity. And they're making their own independent decisions about whether or not they're drinking at water stations. We just passed one. We just passed another one. And that can change their energy. We're following the leader. That's the best runner, but we can also follow others that might be walking or jogging the race. And we can see, they have different paces.
So actually every dot it's like simulating a real marathon runner. And they're gonna have different speed, and some of them have different hydration level, or they might hit the wall.
That's right.
They might change their speed. So it's the actual real life simulation for trying to simulate the marathon.
Yeah, that is the idea. Exactly. And, it's a simplified version of what a real large scale event might be like, but it's a really good way to understand how to incorporate, multi-agent systems into realistic large scale projects.
That is so cool. I really want to learn how those dots, represent connecting to the actual session, and how do you, run them together so smoothly, so fast, and how do you actually simulate different session to map into the actual different type of runner, and how do you design this whole route? Yeah, this is very cool. Wow, can't wait to dive in.
We will definitely do that.
Yeah, I'm Annie. Welcome back to the channel. I will join by Casey West, who is a brain, the builder for the whole system. Hi, Casey. Want to give a quick introduction of yourself?
Yeah, hi. I'm Casey West. I'm a developer advocate, just like Annie at Google Cloud. And I led the development of this agentic system, which we demonstrated at Google Cloud Next for the developer keynote.
All right, Casey. Why don't you walk us through the architecture? I'm really curious to know how this whole cool demo is built. Actually, no, not demo. Cool production system is built.
Yeah, I would call it a reference architecture. It's somewhere between a demo and full production. I'm really looking forward to your community writing better code.
Yeah. By the way, this is all open source. So if you're interested, if you want to play around on your local machine, or you want to try it out, you want to learn architecture, you can always check out the source code on the screen. Let's go.
Yeah.
Casey, can we deep dive in this architecture?
Yeah. So before we get into any code, I want to ground us in the shape of this thing, because this is a somewhat large scale system. So we call it race condition. So race condition is based on 4 layers. There's an Angular front end, a Go gateway, a network of Python based ADK agents, and the infrastructure that those agents live on. So, our first question that I think we need to answer is, why is this a polyglot stack? Why do we have a stack comprised of so many different types of frameworks and languages? And really, it's just because we wanted the best tool for the job. So Go is what we use for a high concurrency traffic cop. It can handle, as many WebSockets as we need, and thousands of messages being passed over those connections without breaking a sweat. And Python is where all the AI lives. So that gives us the access to our entire ecosystem of LLM tools using ADK. And, ADK in Python is a really mature and rich framework. And this separation is why the system feels as snappy as it does. So even with 1,000 agents that are all thinking at once, we still have, the speed and efficiency of the system. So for developers, it means that we can isolate our agent logic in clean Python modules, while the Go layer can handle all the heavy lifting of real-time communication. Does that make sense?
Yeah, so it sounds to me that maybe it's a good a summary can be we have 4 layers. We have front end layer, which have those cool simulation. We have a gateway layer to handle the communication from the front end to the back end, so that we can have 1,000 simultaneous session together because it's more resilient. And then we have a backend layer with ADK Python to handle all the agentic system logic with ADK. And then we have an infrastructure layer with like Redis or PubSub, so that we handle the whole communication protocol and handle the whole as an infra to handle the whole communication system pattern, stuff like that, right?
That's right. That's right. Well, this open source repo has a lot of documentation we've tried to include to help people navigate, but one of them is a system architecture. And this mermaid diagram is where we can start to explain the project. And I know there's a lot here, but let me break it down a little bit. I would consider this to be the one source of truth for the repo about how everything fits together. We can see that the things in blue all live in the browser. So, the user starts by interacting with the simulation UI. We've got some admin dashboards, some other things we'll see later. And then green is what's written in Go. And these Go services are like the backend for front-end systems. If you're not familiar with that pattern, it's where we have a small backend layer running, say, in Cloud Run that the front end can communicate with, and it'll proxy messages back to other parts of the architecture. Orange is all Python. We can see that down here. These are all of our agents. We have a planner agent. We have different types. We'll talk about that soon too. Simulators, runners, which we discussed in our intro. And then we have purple, which is the infrastructure layers. So, the gateway, which is the central layer where everything communicates back and forth, talks to the agents. And it can talk to the agents using 2 different types of transport. So we can have HTTP-based orchestration, but we can also have PubSub-based or event-based orchestration. So we'll dive into how that works as well. Right here, we've got 2 dispatch modes. So the runner agents are the ones that are going to be the highest scale. That's where we might have 1,000 sessions running all at the same time.
I'm so curious about 2 different modes. Like you talk about subscriber mode and just normal callable mode with HTTP call. Maybe you can explain more about that?
Yeah, that's right. So we have these 2 dispatch modes. Internally, they're called subscriber and callable. So subscriber would be this Redis or PubSub mode. And subscriber agents will hold a long-lived Redis subscription. Every tick or every time we sample data when we're running the simulation, the simulator will publish a message on Redis that will go to all of the agents simultaneously, and they'll all wake up and respond. And that allows us to interact with these ADK agents with no HTTP latency, and those interactions can happen in sub-millisecond times.
Wow.
And we only need that for the runners. And that was an optimization that was really important.
Yeah.
But for all of the other agents, the planner agents, simulator agents, and their variants, they are what we call callable. And they just sit there, on agent at runtime in Gemini Enterprise Agent Platform, waiting for an HTTP request. And we only need to do that occasionally compared to the runners. So we can just interact with them using standard A2A HTTP protocol. So A2A being agent to agent protocol. So they just do their work and go back to sleep, and they can scale down to 0 just like they normally do.
I see. So it's like a simulator agent send broadcast a message, say, oh, tick 1, tick 2, and all the runner saw the message at the same time. So they're gonna update the distance, update the location on the map. So is that how it works? So they can see things on Redis,
That's exactly right. And this allows us, to not pay for a bunch of idle CPU for the thinker agents like the planners and simulators, but for the doers, which are sort of the hot path where we have a lot of simultaneous sessions happening, we had to have this efficiency. So this is a really interesting technique that can be reapplied into a lot of other environments. And I think we'll dig into it a little bit later, but each of the runner agents extends the A2A protocol by defining in their agent card, which is another A2A concept, what type of callable methodology they use, or which type of dispatch they use.
Yeah. So I'm curious, before you build the system, do you already design what is the callable, what is the subscriber, so that you can start to configure here, or you gradually figure it out?
That's a really good question. So I gradually figured it out. So I started by trying to do the normal sort of common scenario, which is that we would just do A2A based agents that only speak over HTTP,
Hmm.
because that's how A2A is designed by default. And of course, my goal is to try and use the tools, the frameworks, the standards, the protocols as they are designed. Thankfully, the people who designed A2A also built in a mechanism for extensibility of the protocol. Because what I found out is that there are a number of reasons why this doesn't work when you want to send 1,000 messages to 1,000 different agent sessions at the exact same time, and you want to collect responses from those agents as fast as possible. In our case, we need those responses within approximately 10 seconds. And that might seem like a lot, but it turns out once you optimize your agents and your communication pathways, really the network becomes the bottleneck. And we're going to talk about bottlenecks a little bit later.
Sure.
But basically, I determined that for a couple of different reasons, which I don't want to give away just yet, the runner agents over HTTP would not scale up to meet that need efficiently. And we would have a huge amount of network overhead with HTTP that was unnecessary if we used Google Cloud's memory store service, which is managed Redis. And managed Redis has a pub sub built within itself that can handle, I think it can handle approximately 100,000 concurrent messages incoming per or simultaneously, just with a single node. So even on a small instance, it can handle way more than what I needed. So that was the right choice for sure.
Wow, thanks for sharing your thought process. So essentially you start with all HTTP-based A2A call, and then you realize that it's not suited for the system need because we want 1,000 simultaneous session handled at the same time, and we want to making sure it's a good user experience. Basically, it has the speed is good, the performance is good. So then we iterate to this dispatch, to this subscriber mode, and with Redis to handle the memory situation.
That's definitely right. Yeah, exactly. So I want to follow or continue a little bit. So if we get into the gateway, which as I mentioned is like the high bandwidth message passing layer, the gateway sits between all of the front ends and all of the agents, and all of the messages that pass through go through the gateway. And the gateway is what will read the dispatch mode and try and figure out what to do with it. So in this case, this is just some code that tries to understand capabilities defined in the agent card. So we'll get to agent cards in just a second. In fact, I think I can show you one now. Why not?
Yeah, agent card basically is like an agent identity, similar to our, LinkedIn profile, our name card. Agent also has its card, so that other agent understand what it does, what is the capability, and how to communicate with it, what are URLs, stuff like that. And Casey can show us
That's right.
What is the identity of this agent.
Yeah, so in this case, this is an agent that is running locally. It's on port 9105 in this case on localhost. And this is the planner agent. So how do I know that? So let's see here. The name is right here in this JSON payload. This is the agent card itself. It's the planner agent. You can see that within an agent card, you can define its description. So this is an expert analyst for marathon route and event planning. It has skills. So in this case, one of its skills is that it can create a detailed simulation plan, right? That's what it's supposed to be for. Here are some examples, that sort of thing. So these are all of the skills of the agent. But the thing that I think is really fun is that you can define capabilities and you can have extensions. So I defined an extension using A2A. This is all part of the standard protocol. That was the callable methodology. So how do you interact with this agent essentially? So if you read the agent card and you can understand this, then you can see N26 being for Google Cloud Next 2026, N26 for short. Dispatch, this one is callable. So this is the dispatch method, right?
Yeah.
Is callable. And then if we showed the runner, which let me figure out which port that runs on. Just a minute.
So we can also change this dispatch to subscriber if you want to change.
Yeah, so let me go to port 108, not 9108, and you can see that this is the runner agent, right? And it's a subscriber. So this is the way that the gateway service, it reads this and figures out what what method to use. So if I go back to sharing the code and we look at our catalog, you can see that we're reading the extensions. We're looking for, subscriber, or we're looking for the dispatch method, and then we'll figure out what it is, or we'll default to subscriber because it's the most efficient version. So subscriber is the lowest overhead, so we'll default there. So that's how this code works.
So now I have a much better understanding of the overall, like what are the components, what are the layer, and how they communicate, how we define the dispatch mode. But the next big question is why we want to use this agent to plan the marathon.
Yeah, I mean, honestly, you could write this whole thing as a procedural simulator. You could loop through the runners, call a function for each tick in the simulation. You could write telemetry to a log and you'd be done. But the reason that we reached for ADK was everything around the LLM call. We needed lifecycle management around the LLM. And we also needed sessions to live across requests. We needed callbacks so that we could intercept or interpret model calls and tool calls. And we also wanted things like A to A. So, agents could discover one another without being hard coded into each other's configurations. And we also wanted telemetry and, a dashboard that we could subscribe to. If we built all of that up from scratch, with deterministic code only, it would get really cumbersome. But ADK gives us all of that for free, and it gives us the LLM interaction. So I think that's a big reason why we do that.
I see. So it's not only relying on, just simply using AI, it's also relying on the benefit of using ADK agent, because we can take advantage of the life cycle it actually have, because we can intercept a different part of the life cycle and how we have the communication protocol with agent, and we have telemetry, tool calling and stuff like that. So we can leverage the whole nature of the agent system. So that's a major reason we want to use agent system, even though we have some deterministic logic here. Is that
yeah. ADK gives us all of that out of the box. So, for all of you as a developer, it means that you can focus 100% of your time on intelligence and, the prompts you need to write rather than the plumbing of distributed systems. So that really helped us get a lot of this built out in weeks rather than months.
Cool. I have another reason why I should build this ADK now. Why do you just explain more about the ADK agent so that we understanding better about what is ADK agent, why use ADK agent, what are the benefits we have?
And let's look at an ADK agent right now. So in the code right now, we have the ADK agent for the planner. So this is really it here. You can see that we have an LLM agent in the planner agent.py, and the name is planner. And we have a model here that is wrapped in what we call a resilient model. So this is a little side note, a little tip, but
it's more resilient.
ADK. What's that?
It's more resilient.
It is, yeah. So ADK by default, when it tries to call a model, if that model call fails for some reason, maybe you hit a quota limit, or there was a network outage, or just like a little intermittent failure, it will just fail. But ADK is built on top of Google's Gen AI client libraries, which are the unified client libraries for accessing Gemini models and other models through Vertex AI across the board. So it's a really robust client library for all Gen AI interactions with Google Cloud. And that client library has a lot of capabilities for doing things like automated retries with jitter and backoff. So all of the resilient defensive programming capabilities that we're used to in large scale distributed systems, that's been baked into that lower level client library.
I see.
And you can define a custom model object that basically turns on all those capabilities and then pass that to ADK. So ADK can get those features too.
I see. Is that like auto retry? For example, if I have some 429 quota exceed error, or I have a different error with, for example, image generation that's specific, there's some filter and you need to regenerate. So basically it's handle the redo automatically. Is that a good understanding of resilience?
That's exactly right. It will retry. I built it I designed it specifically to manage the 429s when that would happen from time to time. But then in addition to just retrying, it will also do exponential backoff. And what the other best practice in distributed systems design like this is to do a little bit of jitter. So you just make a small variation in the backoff and the amount of time it takes between retries. So it's not just so consistent. You don't want to retry immediately 5 times in a row. And you do want to back off a little bit and give the network time to catch up or to recover or to heal. So all of that is built into this concept of a resilient model.
Wow.
If I scroll up here,
Yeah, while you're looking for it, I just want to say, no wonder the demo is so smooth, so reliable, even though it's built with AI. It's like, cool. Now I know one trick.
yeah, so I probably should be a little bit better at code search in my IDE, but nevertheless, this is in the code base. So if anybody wants to take this and use it in their own code, they can. But we have under agents, utils, retry.py, there's a resilient model method here. So you give it a model name, and you can also give it some retry configuration and maybe where your model is located, that sort of thing. And it will return this global Gemini object with the model, the retry options that have been configured, and there are default retry options as well.
Oh my God. This is so helpful. It helps the pain point I'm using model for now. This is the
For
first
sure.
thing I'm gonna do. After the session, I will like use this code for my existing agent. And also
That's great. Yeah. So
hair color.
the hair color change helps all development go better, obviously. But in our default retry options here, you can see, just like you were describing, we have the maximum number of attempts, the initial delay, the maximum delay, the jitter, and the exponential backoff base. The other thing to know about this is you saw the global Gemini object. So global Gemini. The reason that this exists is because GCP, Google Cloud, typically only makes available preview models that are not GA yet in the global region and not in specific regions. And ADK, at least at the time of this writing and this recording, doesn't have an easy way to bypass that, especially on agent runtime, or what used to be called agent engine. So in agent engine, we didn't have an easy way to specify that we wanted a preview model like Gemini 3.1 Pro preview or Gemini 3 Flash preview. So you can actually get around that by providing a custom model to ADK. And so that code is in here as well in a global Gemini.py that you can also find in the utils. So this will make it really easy for you to target a preview model, something that's, our latest, our greatest models, and do that on agent runtime. If you were doing it locally, you wouldn't have this problem, but you do have this challenge in agent runtime right now. So this is a way to fix that everywhere.
Wow. Yeah, I did have this pain point as well. I'm using some latest preview model from like a Flash model and Video Nano Blender Pro and the live model. They're all preview in the global location. This is so helpful. Oh my gosh.
Yeah, but this is the whole agent. This is an LLM agent. We give it a name, a model, a description. We give it static instructions. So static instructions or regular instructions or both. This is an ADK feature. Static instructions are they'll never have variables that might be replaced by session state. So they're more likely to be cached using server-side caching with Gemini, which will make your agents more efficient. They'll make them faster, and they'll also make them cheaper because you can have session-based context caching. So I use static instructions here, and then I have a what do we call it? Yeah, a prompt builder that can build a prompt based on some basic criteria. And because this is our basic planner agent, it's sort of the first version of a starter agent. It doesn't take any parameters. It just builds the default profile or the default instruction.
I'm curious, the static instruction, is this automatically inject to the context window? Is that right?
Yeah. So the way that ADK constructs a session history in order to send a prompt to Gemini is that it starts with your static instructions if you have any. And what you want to put in static instructions are essentially any instructions that would be the same across multiple invocations of the agent session or across the board. So that can be the bulk of your prompt many times for many use cases. And that session caching really comes into play on like the third, fourth, fifth turn that you have when you're interacting with an agent session, because the static content was most likely to get cached by ADK, and then you can just reference that ADK and Gemini for server-side context caching. And then you can reference that cache, and the ADK framework has all of the plumbing and stuff built in to already do this for you. And then the next thing that it sends is your regular instructions, if you have any. And those instructions can include variables that can be replaced by session state variables. So if your session has accumulated state variables, they can actually be interpolated, and that'll be sent.
I see.
So those might change on every turn, right? Those instructions might change. So those will be sent. And then, of course, the series of events. So the user message comes next. And then if you have a long running session, you might have additional messages that get sent based on, the agent response and the user response back and forth.
Gotcha. So static prompt is more, it just loaded there for more efficient use, because we have loading more prompt with like prompt with variable injection or like a session state. That's something that's dynamic. So we want to load the static to improve the performance.
That's right. And since we're on prompts, we might as well dive into that too, right? So I actually have that file here. So this is the prompt system for, actually we can start right up here. So this is the planner prompt. And this text here is markdown based, and it's the instructions that instruct the planner to do things like load skills on demand. And the critical concept here is context window management. So when we tell the agent to only run load skills, like right here at line 54, we've got this skills section. We say only load skills on demand. So this allows us to isolate the capabilities of the planner agent into a series of skills. And those skills, which we can also dive into, is instructions and maybe also tools that get bundled with those instructions. And we only want to load them into context when we need them. So in this case, during planning, we only want to load these skills. But if our planner agent is asked about financial information, then we should also load skills based on that. So
it's like
that's how we do it here.
It's dynamic loading so that it's not consume the context window and only use the skill we need. So I'm curious, the skills part, is that how we're going to dynamic loading the skill? Is that right? Is that what it is?
Yeah. So ADK has these load skill tools and a whole series of tools around loading skills. So all we have to do here is instruct our agent. We can say load skills on demand using the load skill tool before calling their tools. So in this case, then we explain, here are the planning skills. We have a GIS spatial engineering skill and a report marathon that has these tools, plan marathon route, report marathon route, that sort of thing. So the idea here really is, and if we looked at the life cycle of the planner agent, when we ask it to plan a marathon route, we would see it do exactly this. We would see that it would call the load skill tool, and that would load the skill. It would get the skill back. It would understand. It would add to its context what tools are available and what instructions it has now, additional instructions. And then it would call the plan marathon route. It would call report marathon. And then this one is interesting. So we also get.
Hi, sorry. Okay, please continue.
That's cute. Yeah, so we also have the ability to get some information from Google Maps MCP server, but only if it's available. So Google Maps MCP server requires you to create an API key for it manually, and there is no automated way to do that. So in order to make this easy for developers who want to explore this code base with open source, I also made it optional. So if we don't have an API key for Google Maps MCP server, then we just won't access or use the Google Maps tooling. And that works with and without. So that you can also see here in step 5, if mapping tools are available, then we can go and look up things like weather data to try and find a suitable time to start our route, that sort of thing.
Yeah, for those of you who don't know what
cool.
is Google Maps MCP server, basically Google has a managed MCP server that help like you easily connect and use Google Cloud Service. And here it's a Google Map MCP server is help you to easily using Google Map.
So you mentioned how do we get the skills? So skills are, and maybe this is a good opportunity to actually share in the code browser here under agents and planner, we have skills, then we have GIS spatial engineering. And so under the skills directory, and by the way, so ADK sets out a directory structure. You can find it in ADK's documentation at adk.dev is the new URL for ADK documentation. But you can find it there as well. And you can see that for GIS spatial engineering, we've got the skill.markdown file. So if we look at that, we can see, let's kill that. So for the skill.markdown file, we can see that its name is GIS Spatial Engineering. And in the description, we say, use this when the marathon needs to plan, a specific route. So it tells your agent, this is context that gets loaded into your ADK agent when you load this skill. That explains how to use or when to use this skill. And also there's metadata that explains what additional tools will you be loading into this agent now that you've loaded this skill. So this lazy loads tools as well as context. And I think that that's a really important feature. I know skills are kind of all the rage now. Everybody wants to build skills for everything, but this is how you can build skills for, agents that you'd be running in production environments.
So with this, we can lazy loading the skill without ADK know how to when to load the skill and how to load the skill.
That's right. And of course, in our prompt, we explained on step 2 for the planner, we said load the GIS skill, and we gave it an example of how to do that. There's also some code in, loading ADK tools where we can go and find our skills and just make sure that we understand what our skills are. I mentioned ADK has these features built in. So ADK has the skill toolset capability. So we can read the metadata about those additional tools and also load those in a lazy way here. So there's a little bit of code in here to check that you can check out for how to do that as well.
Cool.
Yeah.
Also, another thing I'm very excited to try right after the session. Keep adding to my to-do list.
I know there's so many things to talk about here. Let's see. There's also, how do the agents communicate over the gateway to the front ends? I think that's maybe another important piece. This is a large file. It's probably too big. So again, I'll be looking for PRs if people want to help me refactor my code base. That would be amazing for me.
Please, everyone, if you're watching till now, please help Casey, help us improve.
Yeah, exactly. Yeah, so this is under agent utils and it's called communication.py. So this is loaded into every agent, but this is really the last code stop for this section, I think. When the planner needs to call the simulator, for example, these are two different agents. And I chose to use this call agent tool that I loaded everywhere as a wrapper around A2A based interactions. So this abstracts away the networking because what we're actually doing is sending messages to the gateway service that we talked about before. And the gateway service is routing those messages and sending them to the correct agents. And as you get a larger scale system, one of the things I wanted to be true about this multi-agent system is that if they needed to or wanted to, any agent could communicate with any other agent in the system. So you can think about it like a mesh network for agents, as opposed to like a directed graph where only an agent only talks to another agent based on a predefined workflow. I wanted to have the option for all agents to communicate with one another. So the planner doesn't know where the simulator is running at all, right? It just says, using this call agent method, it just says call the simulator, right? And then ADK through this communication layer handles the discovery. It'll retry if it needs to, if the agent didn't respond right away. And maybe one big reason for that might be a cold start. If you are scaling these agents to 0 and they haven't been sent a message for a while, they might time out on a cold start. So you might want to try again. And then, so it'll send the message, it'll retry, it'll emit the pulses or the messages to the gateway for telemetry as well. So we'll see that in dashboards. And this is like the single entry point for all agent to agent chatter. And it just wraps A2A in this really reliable function call or tool call.
That's pretty cool. So only callable agent will have cold start, right? For the subscriber, they're always subscribing. So they don't have cold start.
Typically, that's certainly how I did it. So I decided that because the runner agents needed to respond instantly to any messages, I had at least one hot instance always running. And the runner agents actually were deployed to Cloud Run instead of agent runtime because I had more control over the scalability characteristics of services running in Cloud Run than we currently do with agent runtime. So Cloud Run has just more tweaks and knobs to dial when it comes to the way we deploy them. We can configure specific concurrency configurations and hot and cold instances up to our as many as we want almost. I mean, there are real limits, but we weren't close to those limits because Google Cloud can handle a lot.
Yeah, well, you say you want to have the meta network so that every agent can call, like potentially connect to another agent. That's why we want to wrap a call agent with A2A protocol. So how does the is that why, first of all, you haven't defined a workflow agent, you define a workflow prompt, and secondly, who decide which agents interact with another agent?
Yeah, so the workflow prompts and were because LLM-based agents needed to make decisions about how to execute the workflows. A big reason for that is because we were building a multi-agent system using Gemini as a core tool to demonstrate these capabilities.
Okay.
I mentioned before that like we could have done this fully deterministic, but then we would have had a lot more work on our hands. But in the end, even though every agent could talk to every other agent if they wanted to, what ended up happening, of course, and this is, I think, true of most real systems, is that we had some predefined or some clearly defined workflows that existed that kind of made the communication structures more visible. So, and more deterministic, I suppose, is maybe a way to say it. So we always knew that the planner agent would need to do evaluation and talk to the simulator agent when it's planning a marathon. And then when we want to run the simulation, the planner agent will ask the simulator agent to run it, and the simulator agent will communicate with the runner agents. So we kind of established that early on, but if we had more time, a larger vision of this thing, which actually is in the README of the project as well, for ideas to expand it. So again, I'm looking for, pull requests and contributions from the community would be awesome. But a larger vision of this is that we had even more agents in the mix that might be able to interact with one another. So a good example would be if we had a public service or a public safety agent that was maybe trying to make sure the runners were safe from traffic and that the cars were not going to cross the marathon route when they were trying to drive across the city. Or if we had businesses represented as agents that might be impacted by the marathon. So if you had a drive-through food service business and the marathon closed your street, that would be bad for your business maybe. But if you had like a walk-in coffee shop, that would probably be very good for your business. And it would be interesting to model that as well. We never got that far because we had a limited amount of time and a limited amount of scope. But in those cases, we could have agents interacting with one another directly. Maybe a runner jumps off the route and goes and gets a coffee, or maybe a runner tries to cheat and cut across a street and try and win that way. Like it would be interesting to try and catch them and see what happens in those scenarios. So
yeah, it's like a movie or a game. Yeah. That's so fun. Yeah. So
well, what's cool about having an LLM in the mix is you can get chaotic and unexpected behaviors. You still have to sort of prompt the possibility of that. Mm-hmm. But I think it'd be really interesting to expand the runners with a sense of identity where maybe a runner like follows the rules and has been training really hard, and maybe another runner wants to cheat, and we could, write that into a prompt and see if they could get away with it. And then we might have to have like other agents that are looking out for cheaters and seeing if they can find them.
Yeah.
So that's the architecture for this episode, but we skipped the most interesting decision of all. When does the system actually use AI, and when does it skip LM entirely? So in the next episode, we will see how does it scale to 1,000 agents all at once. Alright, I will see you in the next episode. Bye!
1,000 AI agents running a marathon. Once the race starts, almost none of them use AI at all. Hi, welcome back to Hands-on AI. I'm Annie, and I will join by Casey West. Casey West is from Google Cloud, and he led to build this entire agentic system. And what you're looking at right now is 1,000 AI agents running a marathon. It's open source code, and you can check the link on the screen. So each one of them is real and independent. They're all running at the same time. In the last episode, we built the architecture, and today we are going deeper into the decision that making running 1,000 AI agents actually affordable.
So I think, Annie, this is the juicy part. So like, when do you let an LLM decide and when do you write code? And I think it's one of the more important architectural decisions that we have to make. So if we're back here and we'll go live, because why not? What could happen? What bad could happen in a live demo? But let's go ahead and plan a marathon route. It's actually working. So it's doing what we were discussing earlier. It loaded the GIS spatial engineering skill. It's going to plan a marathon route. This takes a little bit of time, but here we go. So we have a marathon route that gets planned. Cool.
Wow.
And the regular planner agent just outputs this text.
So it's loading a skill that is using a tool, load the skill. So it has knowledge of GIS spatial engineering, and then it's planning the route to actually planning the route. So, oh, cool.
Yeah, exactly. So here's the route that it planned, right? And interestingly, we had a lot of constraints on how to plan this route. But we knew, for instance, it has to be 26.2 miles long. And it also has to be on a city-approved street network. One of the things that we decided to do here is that this 3D visualization that you see for Las Vegas is very beautiful. However, we couldn't model every single street and every single building in Las Vegas, right? Let me just show you in GitHub because it does a really cool rendering of this.
Wow.
We have a GeoJSON file. And if you go look up GeoJSON, it's a standard. It's a JSON payload that will show like coordinates and properties, features, that sort of thing of a map. But you can see here in the blue color that these are all of the roads that are actually available to us to run this marathon route on. Now, again, if you were building a real marathon in Las Vegas, you'd have access to all the roads. But again, we had a limitation. So because of that, if I zoom out again, you can see that we only had a subset of the roads available to us in Las Vegas. So that was one issue that we had. So because of that, we couldn't use Google Maps to just give us a marathon route. The other limitation is that even if we wanted to use Google Maps has two route modes for between destinations that might be interesting. One of them would be cars or driving directions, but driving directions honor things like one-way streets, where if you're running a marathon, you can close the street down and run in whichever direction you want, right? And then if we were going to use walking directions, there's a unique challenge with Las Vegas, which is that walking directions will frequently bring you over bridges, like walking bridges over major roads and through buildings.
Yeah.
Do you remember? So like it would be very unlikely that we would build a marathon route that would make you run through the Luxor, for example. The next thing that people were really interested in is, could we just have Gemini build a route for us?
I would rely
based on. Go ahead.
I would have a very smart algorithm to like making sure it has an efficient path. This is similar to my interview question to like find a route between two different points. And then I think I would rely on the deterministic logic, but I think LLM definitely can give a good route. But if I make a decision, my intuition is more lean towards deterministic logic because it's more reliable and it's give you more optimal solution.
What's funny is, not to give too much away about the interview process here at Google, but at least for our role when I'm interviewing, I ask a question about how would you use AI to solve a particular type of problem, and the best answers are not to go with full large language models in my interview question, and it turns out that's true here as well. So, doing a shortest path or a nearest path solution is actually extremely difficult. We would call it an NP hard problem. It's one of the harder problems in computer science. But you can see how noisy this is. And for those of you, and I think, Annie, you've probably done this, if you tried to give this to Gemini, it might be able to understand it, but it's going to be very noisy and very difficult for it to like keep track of and keep context of as you add more instructions. But basically there's an algorithm out there called a spine and sprout algorithm. Yeah. So phase one, as I mentioned, is this Dijkstra algorithm that takes the road graph. It uses what's called a Haversine weighted edges to stitch landmarks together. Then phase two is extending the path with a serpentine waypoint. And we use then we also have to, so we do the serpentine waypoint, which will have a series of sequences. And then we have to trim the last segment of those sequences so that we get to exactly 26.2188 miles. That's the specific amount of distance for a marathon officially. So this is deterministic for sure. So building the route itself is deterministic. And very importantly, it's also unit testable. This is all a bunch of gnarly math. So this is why I felt it would be most valuable not to use Gemini and to, in fact, just make this part deterministic, is that all of this is computer science algorithms to solve NP-hard problems that, have been built over the last several decades. Now, where I did end up using Gemini is in figuring out which algorithms to use. We used AI Studio because it was just fast enough, but also it was easy enough for us to do two things. So one of them is code execution here. Let me make sure my screen is big enough. So we used AI Studio in this case because I also had non-developers who were also trying to figure out what would the best algorithms be. So what we did is we uploaded from our files, the network.json file. So that was the GeoJSON file that I showed you earlier with all of those coordinates in it. And then we described in our prompt all of our constraints. And then most importantly, we enabled code execution here. And that allowed us, and we could also do grounding with Google search. So these two things allowed us to have Gemini in AI Studio. Let me just click that button. Gemini in AI Studio was able to look up algorithms for solving problems like this using its search tools and its own knowledge, and then write Python code using code execution that we could use as a starting point.
Wow.
I then took that and I brought it to tools like Gemini CLI, and I said, here's a starting point. Might not be perfect. Here are our constraints. I want this to be unit testable. I want you to do deep code review on this. And we iterated on these algorithms a number of times to get to where we are today.
That is so smart. I will try this way to do research next time. So the routing logic is fully deterministic. But this is the interesting part. Casey still used AI to help choose the deterministic algorithm, just not at runtime. And that is a pattern behind this whole system. We use the model where it actually helps, and we skip the model where it doesn't. They applied that same idea again inside the simulator, and that is where the real trick lives.
So that's how we determined it in the planner agent, right? And then there's two other locations where we had to make similar decisions. The simulator is an agent, but what if the work is really mechanical? But it lives inside of an agent framework. So you still want an agent lifecycle, right? And you still want things like A2A to communicate with it. You still want telemetry, but you don't want an LLM call for something that might be a deterministic or a procedural set of steps. And you've written a bunch of agents before, Annie, so sometimes you write a bunch of tools that have your deterministic logic in it, and all you really need an agent to do is call tool number 1, and then call tool number 2, and then call tool number 3, right?
Yeah.
Yeah. So the question is, do you want an LLM to do that, or do you need an LLM to do that?
Depends on the use case. If sometimes for the case that you do not want to add deterministic logic, it's good for LLM to decide, because sometimes you cannot handle all the cases with different user input. Then I think LLM decide is a good approach, especially cover different edge case. And then if it's a specific use case, for example, I just want a planning, for example, specific route, I might just want to add deterministic logic to bypass the LLM generation, and I just add some deterministic logic to force it to do a certain thing. And I actually have to do this trick for some of my agent system, that I have to use callback with before to call to bypass something, and then to do some other deterministic logic in the backend. Yeah. It's really depends on use case for my situation. I'm curious for this use case, how do you handle that?
Yeah, so in this use case, the simulator agent's really fascinating because there are a couple of things where we might want the LLM to be a part of decision making, right? Some heuristics, that sort of thing. But to run a simulation is a relatively straightforward approach. You need to set the simulation up, you need to run the simulation itself. And to run the simulation, what we chose is essentially, we call it like server-side ticks, which is a term built from like game development. So like in games, when you have a server, a centralized server, it usually has a tick where every couple of milliseconds or every second, it will essentially try and figure out the state of the entire system and it keeps track of that state. So that's what we did here as well. So you can think of the simulator as like the game server, and you can think of the runners as little game players that are all running around inside of the game. And so the simulator is trying to figure out, where are all of my runners? What is their current state? What are their properties? So that's what we did here. So here you can see the architecture of the simulator agent, and this is inside of the agent.py for the simulator. So we still want to use the agent paradigm or the agent's model to organize the complex workflow, but we want to cheat time as much as possible and be as efficient as possible on the execution. So if we go down to pre-agent, see pre-race agent here, this is the trick. So pre-race agent and the tick agent are both LLM agents, and they have a model. But if we look at line 252, you can see in this comment here, the model is required by the LLM agent in order to create the object, but it's never actually called because the before model callback, this is an ADK feature of callbacks. The before model callback intercepts every invocation and returns deterministic tool calls. So in this case, the pre-race thing just needs to set up and call a couple of tools in order to set up the environment.
Wow.
I knew it needed to do the same thing every time, but I still wanted to have it function exactly like any other ADK agent. So I could get the lifecycle management, I could hook into the callbacks, I could get the telemetry, all that stuff.
Wow. So before you even using the model, you have this callback, intercept this lifecycle, and then just switch to your deterministic logic to bypass the actual LM use.
That's right.
That's so cool.
And this is important. It saves money, it reduces latency, and it guarantees reliability in a part of the agent system where we actually need it.
I did a similar thing with one of my Gemini live agent that, when in the voice context, if you have a live agent, like have voice in, voice out, with tool call add latency so that the voice is not as fast as not using tool call. So I basically also use it before tool callback to bypass the tool call so that it will return to me immediately.
I'm also still adhering to the ADK paradigm. Function call will still set up a tool call using ADK's own client libraries and publicly provided interfaces to do the exact same thing. And we can even set session state, context state, that sort of thing here. And that's exactly how this works. Yeah. So, and it's the same thing in the ticks. So I mentioned the ticks as well. If I scroll down a little bit here, like we can see the tick callback does the same thing. The tick callback only ever needs to call advanced tick and check if the race is complete. And because I know that that's all it has to do, I want to cut down on any latency. I don't need the LLM calls. And just because of the runners especially, and because of all of the things that are happening when we run the simulation, there's already a huge amount of context and like messages being passed to Gemini. So any places where we can optimize it, this cut down on the time and space. So this is a really efficient model where you do have some areas in a code base where they need to be deterministic. You can get away with that even within a framework like ADK and still adhere to ADK and get all of the features that are available to you. It would be easy to write this where you short circuit like tool calling and your callback does all the work by itself, but then you lose things like visibility and telemetry. So I would recommend to anyone out there, if you feel like you need to do a similar thing, use a model like this and tear apart this code base and steal it for yourself.
That is so cool. So I feel like it's a agent surface, but below the surface, it's the deterministic normal, deterministic logic, deterministic code. Do you think it's still an agent?
Yes. So the the simulator agent is our most sophisticated. Like it's in ADK, we would call it a multi-agent system, even though this whole thing is like many independent agents that are like network disconnected from one another. The simulator agent actually has, in ADK, we call them workflow agents. So it uses a looping agent, it uses a sequential agent, things like that. So it is a multi-agent architecture with sub-agents. So I still think it's an agent, even if some pieces are deterministic.
Yeah, this is really cool because I've been struggling a lot with how do you build a hybrid system while you still keep the advantages of agent system, but also adding more control and basically have a good balance of use determinist logic when it needs to, but rely on AI for when AI is doing the better. When is the time for AI to doing a better job? So how do you build a hybrid system? I think this is a really cool way for us to, first, we have all the benefit of ADK agents. We have benefit of life cycle, this tool call, with telemetry, observability, and more. But at the same time, we can adding determinist logic bypass the model callback. It's really cool demonstration of how you can build a hybrid system, how you can really have a good balance of both. It's really cool.
Yeah. Thank you. We did the same thing with runners just briefly. So the runner agent uses an LLM, but the runners we have a lot of them. That's our most scalable agent in terms of how many we're trying to run or simulate at the same time.
Yeah.
And any latency is going to be a problem. So we also built what we called the autopilot runner, which you can see on screen here. Mm-hmm. And it just extends or augments the behavior of the regular runner agent. So that's what get base agent does here. But then instead of calling the LLM, it makes its own decisions using some heuristics and a bunch of data that we pulled from Gemini Deep Research about how runners behave. So it's all code based, but that allows the autopilot agents to run within milliseconds whenever they get called. And that's how we could get the back end can support up to 10,000 simultaneous agents. The front end is this very beautiful 3-dimensional visualization, and it's constrained by Chrome and memory management, CPU and GPU. So we were only able to show 1,000 on the screen during the demo, but that's how we got to that scale.
Cool. So you talk about you're showing 1,000 agent session at the same time. And I know that now we cover, we understand architecture, we are deep dive into the agent code, we are understanding how it loading the skill, and we're understanding how to balance the LLM and the deterministic logic. But still, what is the real magic behind the scene so that all the 1,000 sessions can run at the same time? What is the trick?
Yeah, that's a great question. So I think to do that, I want to just dive in a little bit to things like the agent lifecycle so we can see how things work. So what we're looking at right here is one of the developer tool UIs that we built into Race Condition. It's the agent telemetry dashboard. And we can see actually some messages that are coming in right now. What you're watching is every row is a real ADK lifecycle event from a real agent session. And we have rows that say like starting and finished or model start, model end, that kind of thing. And we also have them grouped by session IDs and the sequence of the message within that session. So this is pretty cool. I think a thing to know is that all of these are also messages that are passed over the gateway using PubSub as a broadcasting mechanism and then get emitted over a WebSocket to this front end UI. So if I click run simulation now, this is live. We should hopefully see messages. Yeah, so the user said run a simulation, right? That was me. So that's what we're doing there. And now we can see that the planner with eval is doing a lot of the heavy lifting right now. It'll be interesting to see how fast this is considering, Gemini latency and API calls and all of that. But now we can see actually a number of agents that are running, including these runner autopilots. So they all got messages. Let me see if I can scroll to like tool end from process tick. So the simulator agent has a sub agent that is a tick processor, right? So it sends a process tick message event to the runner autopilot agent. And we've already scrolled past it here. We can see this is how many events are running in the system live. And we can see things like latency and total events here, total number of tokens. So Gemini 3 Flash Preview has 350,000 tokens. So as you can see, this is a decent amount of work, right?
So you're looking at about 350,000 tokens, and that is not zero. But here is the key. Those tokens are not from the route math. The route math is deterministic code. So that part is basically free. The token come from the AI doing judgment. Which landmarks should we include? Does the timing make sense? Is the plan safe and runnable? The model reasons through that once, and then before the race. And then 1,000 runners just take over. And they actually never call the model itself. So adding more runners does not add more tokens. The AI decides and the code runs.
So this is the fire hose of everything that's happening in the system. And with 1,000 runner agents, it means that we've got these 1,000 independent ADK sessions, each one with its own state, right? And we happen to be running this on Cloud Run, but these processes are stateless. And we have, to run the real system in production, we had over 50 instances of the service for runner autopilot on Cloud Run. So that's 50, unique server processes that are running on Cloud Run, all stateless. So session state has to live somewhere, and it has to be shared because these runners are keeping track of the sessions throughout the history. You can see that this is the 67th turn on this session for this runner. This is one unique runner. And really, that was one of the first things that broke for us. So when you're building a scale for stateless sessions where you have to do large scale, one of the first questions is, where does the state live? I think we have to talk a little bit about ADK and session stores. So ADK by default comes with a handful of session stores automatically available. Andy, do you know which session store, when you're running ADK locally and you're just developing your own agent, which session store it uses by default?
Yeah, so ADK has in-memory session service, basically using the RAM, and it also have the option like database session service. You can use your own database solution, for example, AlloDB or SQLite, Cloud SQL, stuff like that. And then there's also option called Whereas AI Session Service. You can using our agent runtime. I'm gonna pass it back to you, Casey. So how is the system using memory? How does the session service configure here?
Yeah, exactly. So first of all, very thorough response. I love that. And you're right. So we had a couple of challenges with the default options that were available to us in ADK. In memory doesn't work when you have multiple instances of your agent running at the same time, like 50 instances on Cloud Run, because then your session state is only localized to a single instance. And I needed to share the session state across all those instances because we never know which one the global load balancer will give the next message to. But I also couldn't use what do we call it now? The agent platform sessions in Gemini Enterprise Agent Platform, because this agent was running on Cloud Run instead of running in agent runtime. And it was running on Cloud Run so I could get the scalable characteristics I needed.
Yeah, but it takes time, right?
What's that?
But it takes time to loading this, right? I think the run is only faster.
Yeah, so the third option, of course, would be like a database like AlloDB, and I did try that. But the overhead of the SQL calls, the queries to retrieve and store session state and the transactions that were required were actually too slow, and they became one of the bottlenecks. So I had to come up with a creative workaround. So one of the techniques I was using in this architecture already to try and keep things fast and with really low latency was using Google Cloud's memory store, which is managed Redis. And so my question was, could I use Redis as a session store? Well, ADK doesn't have that by default. But what I found that I really was very happy about is that there is a repo that Google maintains with community contributions called Google ADK Community. You can find it on GitHub. And in Google ADK Community is a Redis session service that a community member had written. Wow. So I used it. And then my agents were as fast as I needed them to be. So that was one of the key things that I was able to do.
Kudos to that community contributor.
Yeah, exactly. I was really, really, really pleased with that. And then just to give them like a shout out here, all you have to do in your Python code is pull in the Google ADK community repo, and then you can configure your session service. In this case, the Redis session service in my repo is a subclass that does a few extra tweaks just for a little bit of additional performance, which is that it prunes events and prevents blob growth. So just making sure that we keep everything as streamlined as possible, because again, I have 1,000 simultaneous sessions. We send them all a message over PubSub instantly and get all the responses back, and we have to collect them as fast as possible. There's way more to go into with this, and there's maybe not enough time, but that's where I will encourage everybody to explore this code base. And let me actually just share with the community, everybody who's listening, one of the ways you can explore this code base, whether you're using things like Claude Code, Cursor, or like Gemini CLI, is that it includes skills for your AI harnesses or AI dev tools, including and exploring the code base skill, which will explain to your AI coding assistant like Gemini CLI how to look into this code base, where things are. And then you can ask a question like, how did we get a highly efficient Redis session service for extremely low latency, scalable sessions with agents?
Wow. No wonder when I studied this repo, my AI is really efficient with all the answers.
Yeah.
Oh, thanks for, creating those skills. That's pretty helpful. Thank you for this great session, Casey. I've learned so much from this conversation.
Thank you.
And
I had so much fun exploring it with you again.
Stay tuned, and we have more episodes coming up. And again, thank you so much for watching this, and I'll see you next time. And bye.
Bye.